You know, when you start learning about data structures and algorithms, specifically sliding windows, almost everyone teaches you the fixed window first. And it's like a fixed window is basically like a rigid box.
Yeah, a totally rigid box.
Right. You slide this unchanging box across your data, looking at, three items at a time, then the next three, then the next.
It's very predictable.
Yeah.
Like you always know exactly how much data you're holding at any given millisecond.
But then you encounter the variable window. And a variable window is, well, it's not a box. It is a rubber band.
I love that analogy.
It stretches to include more data, pulling and pulling as far as it can go, and then suddenly it snaps back and shrinks to stay valid.
And that transition, from the rigid box to the dynamic rubber band is the master pattern shift. It's the underlying architecture used in streaming systems, real-time analytics, and frankly, it is the secret to passing some of the most advanced coding interview questions you will ever face.
Which brings us to our anchor problem for today's deep dive. If you are preparing for an engineering interview, you have probably seen this classic. It's find the longest substring without repeating characters.
Oh yeah, everyone gets this one.
Right. So imagine I give you a string of letters. Let's say the string is ABCABCBB. The output you need to return is simply the number 3.
Because the longest consecutive sequence of totally unique characters is ABC or BCA or CAB, which all have a length of exactly 3.
Exactly.
The absolute split second you hit that second A in the sequence, your substring is no longer entirely unique. The rules are broken.
So before we go any further, I want you, the listener, to do something. Pause and think about how you will solve this interview coding question.
Yeah, really think about it.
Ask yourself, when should we expand the rubber band? And crucially, when should we shrink it?
It is a fundamental tension. Think about how you would manage that stretching and shrinking conceptually, before you even think about writing a line of code.
While you think about that, let me officially welcome you. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
And today's deep dive has a very specific mission. We are going to master dynamic window control.
That's the goal.
Right. The goal is that by the end of this conversation, you can walk into any AI or ML engineering interview, look at a complex substring problem, solve it optimally, and communicate your logic exactly like a senior candidate.
Communication really is half the battle. You can't just silently whiteboard a solution. You have to explain the mental model.
Exactly.
And now that you've paused to consider our anchor problem, let's unpack the intuitive mental model you need to solve it. You call this concept the 2 roles.
Yeah, the 2 roles. So we implement the rubber band using 2 pointers. Imagine them as 2 distinct personalities working together on the same problem.
Okay.
Your right pointer is the optimist.
Okay, the optimist. I'm guessing its job is just to keep pushing boundaries.
Pretty much.
It wants to include more data, so it constantly moves forward step by step, reading through the string.
That is its entire motivation. The optimist believes the window can always be larger. It just keeps grabbing the next character and the next, expanding the rubber band.
Just blind optimism.
Right. But eventually, the optimist goes too far. It includes a duplicate character, or it exceeds a target sum, or it breaks whatever specific constraint the interview problem gave you.
Oh, I see.
And that is when your left pointer steps in. The left pointer is the realist.
The realist comes in to clean up the mess when the optimist gets too greedy.
Exactly. The realist fixes violations by shrinking the window from behind. It moves forward, contracting the rubber band, discarding elements from the back of the window until the rules are no longer being broken.
So there's a golden rule here, right? At any given moment, the space between the realist on the left and the optimist on the right, well, that window always represents the best valid substring so far.
That is the core invariant. If you keep that golden rule in your head, the logic practically writes itself.
I want to try an analogy here, just to make sure this dynamic really sticks. Abstract pointers can be, kind of slippery to hold in your head.
Oh, definitely.
Let's compare this to packing a suitcase for a long trip.
I love a good physical analogy. Go for it.
So the optimist, your right pointer, is you enthusiastically packing. You're throwing in shirts, shoes, a heavy winter jacket, like 3 books you probably won't read.
Sounds like how I pack.
Same. You just keep shoving items into the suitcase, expanding your collection. But the suitcase is our window, and it has a physical limit.
A hard constraint. The bag has a maximum capacity.
Right. Suddenly you try to zip it, and it won't close. The condition has been violated. The bag is overstuffed. Now, the realist, your left pointer, has to step in.
Okay, so what does the realist do?
Well, the realist doesn't just throw the whole suitcase away and start over. Instead, they start taking things out one by one from the bottom of the pile. Do we need the heavy coat? No. Do we need the third pair of shoes? No.
I see where you're going with this.
The realist keeps shrinking the pile just until the exact moment the suitcase successfully zips.
And notice the sequence of events in your analogy.
Mm-hmm.
The optimist operates continuously, adding and adding. The realist only activates when a condition breaks.
Ah,
And the realist only does exactly enough work to restore order. Once the suitcase zips, once the window is valid again, the realist stops. And the optimist takes over again to see if maybe, just maybe, we can squeeze one more tiny thing in.
So, knowing how the rubber band stretches and shrinks, or how the suitcase gets packed, is conceptually great. But here's where we hit the real challenge.
The code.
Yeah, the code. How do we translate this conceptual optimist and realist into an algorithmic structure without failing the strict efficiency tests of an interview?
Let's break down the logic conceptually, starting with a simple set structure for our anchor problem. So, finding the longest substring without repeating characters. We need a way to keep track of what is currently inside our window.
Since we only care about whether a character is a duplicate or not, a set is perfect. It just answers a simple yes or no question like, is this item already in the suitcase?
Exactly. So we initialize our empty set, we place our realist pointer at the very beginning of the string, and we keep a tracker for the maximum length we've seen so far, starting at 0.
Okay, got our variables set up.
Then we unleash the optimist. We set up a for loop that sends the optimist marching through the string, character by character.
For every new character the optimist encounters, it asks the set, have we seen this before?
Right.
If the set says no, we are golden. The optimist tosses the character into the set, we calculate our new window size, and we update our maximum length tracker if this is a new record.
But what happens when the optimist grabs a character and the set says, yes, we already have one of those? That is our condition violation. The suitcase will not zip.
This is where the realist has to go to work. We need another loop inside our main process.
A while loop.
Yeah, a while loop. As long as that specific duplicate character remains inside our set, the realist has to inch forward from the back. It grabs the character at the left edge of the window, tosses it out of the set, and takes a step forward.
It repeats this, discarding and stepping until the duplicate is finally gone.
And that single moment of the suitcase finally zipping shut, that is the exact moment the inner cycle ends, the window is valid again, and the optimist is allowed to add the new character and continue.
Perfectly said.
Wait, stop there. I need to push back on this because my algorithmic spidey sense is screaming right now.
Uh-oh. What's wrong?
You just described an inner cycle running inside an outer continuous process, a while loop nested inside a for loop. Doesn't that immediately mean our time complexity is O of n squared?
It sure looks like it.
If I write a nested loop on a whiteboard, an interviewer is going to fail me for performance. Won't this fail the optimal solution test? How is this optimal?
So that is the classic interviewer's trap. Visually, yes, there's an inner loop. But mathematically, the performance is strictly O of n.
Wait, really? How?
To understand why, we have to use something called amortized analysis.
Amortized usually means spreading a cost out over time, like a mortgage. How does that save us from O of n squared?
Think about it physically. Imagine the sliding window is a fenced-in area at an amusement park, and both the optimist and the realist are working the turnstiles.
Okay, I'm with you.
Every single character in your string gets exactly one ticket to enter the park and exactly one ticket to leave.
One ticket in, one ticket out.
In the absolute worst-case scenario, the optimist scans a character and adds it to the window. That's one operation. Later on, when a violation happens, the realist might scan that exact same character and remove it from the window.
That's the second operation.
Right. A character cannot be added twice. It cannot be removed twice.
Yeah.
It enters once and it leaves once.
Ah, oh wow. So even if the realist suddenly has to process like 5 characters in a massive burst to clear a duplicate, it's just spending tickets that were already paid for. No character ever buys a third ticket.
And that means if your string has 1,000,000 characters, the optimist takes 1,000,000 steps forward, and the realist takes, at most, 1,000,000 steps forward.
So 2 million total.
Exactly. The total number of operations across the entire execution of the algorithm is at most 2n. And in big notation, we drop constants.
Oh, right.
So that 2n drops down to strictly O of n. The inner loop does not run n times for every step of the outer loop. It runs a handful of times across the entire life of the algorithm.
That is such a profound distinction. You are looking at the total cost of the algorithm spread out over time, not just assuming the worst possible single step happens on every iteration.
There's a huge shift in perspective.
Explaining amortized analysis to an interviewer instantly proves you understand how the machine is executing the logic, rather than just memorizing syntax rules.
It really separates the junior developers from the engineers. Now, that covers time complexity. But we also have to consider space complexity. How much memory are we eating up with this set that tracks our characters?
Well, the space complexity would be O of n and m, right? Where n is the length of the string and m is the size of the character set.
Break down why it's the minimum of those two.
Well, the set can only grow as large as the string itself. If your string is 3 letters long, the set maxes out at 3. But it's also bounded by the total number of possible unique characters that exist in your alphabet.
Which brings up a massive pro insight. What happens if the interviewer explicitly tells you, hey, the input string will only contain lowercase English letters?
Oh, if it's only lowercase English letters, your character set size, m, has a hard limit of 26. And since 26 is a constant, your space complexity drops to an incredibly efficient O of 1 constant space. No matter if the string is 10 letters or 10 billion letters long, your set will never hold more than 26 items. Pointing that out during an interview is a huge flex.
It really shows you are listening to the constraints.
So a set is great for simple yes or no questions, but the real world isn't always binary.
Rarely is.
What happens when a problem allows for some repetition? Say, a network log that allows up to 5 failed logins before triggering an alert. A set cannot count to 5. It only knows if a failed login exists or doesn't. How do we adapt our rubber band for that?
That is when you must upgrade your toolkit. A set is fundamentally limited to tracking presence. To level up, you switch to a dictionary or hashmap, which allows you to track counts and frequencies.
Okay, so moving from set to hashmap.
Right. Instead of just asking, is there an A, the hashmap answers exactly how many A's do we currently have inside the window.
And how does that actually change the mechanism of the sliding window?
It changes the causality of the realist's behavior. When the realist moves forward to shrink the window, it doesn't just delete a character from the map entirely. It decrements the count.
Oh, I see.
If the problem says no more than 2 duplicates, and your window currently has 4 A's, the realist removes 1. The count drops to 3.
But 3 is still greater than 2, so the condition is still violated. The suitcase still won't zip.
Exactly. The realist has to loop again. It removes another A. The count drops to 2. Only at that specific threshold does the alarm bell turn off. The condition clears, the inner loop breaks, and the optimist is allowed to move forward again.
The moment you introduce a frequency hashmap into the variable window pattern, you unlock a massive library of advanced problems. What are the cheat codes here? Like the trigger words a candidate should listen for to instantly know they are dealing with a dynamic sliding window hashmap problem.
Listen for adjectives that imply a maximum or minimum boundary combined with a contiguous sequence. Words like longest substring, shortest subarray, or without repeating.
Okay, those make sense.
But the ultimate trigger phrase is at most K.
Oh, find the longest substring with at most K distinct characters.
The moment you hear at most K, you know you need a frequency hashmap. The realist doesn't shrink when it sees a duplicate. It waits until the hashmap grows to contain K plus 1 distinct keys.
Ah, one too many.
Right. Then it shrinks, decrementing counts until one key's count hits absolute 0 and drops out of the hashmap entirely, bringing the total unique keys back down to K.
This sounds intricate, but there is a general variable window template, a master blueprint that every candidate should just burn into their memory. Let's walk through the conceptual steps.
The master template is surprisingly simple. Step 1, initialize your trackers. Place your realist pointer at 0 and set up your empty hashmap.
Got it. Left pointer at 0, empty dict.
Step 2, start your main process. Let the optimist continuously expand the window to the right using a for loop.
So for right in range.
Yep. Step 3, update your hashmap with the newest data the optimist just found.
Add it to the pile.
And then step 4, the inner cycle. Check if the condition is broken. If it is, decrement the count of the character at the realist pointer and shrink the window from the left.
By doing left plus equals 1?
Exactly.
Yeah.
And finally, step 5, once the inner cycle finishes, your window is valid again. Compare your current window size against your best score and update your answer.
Step 4 really is where the magic happens. Which brings us to our second pause. I'm going to ask you, the listener, a direct question. Pause. What decides when to shrink?
Think about it.
What is the exact trigger for that inner cycle to activate?
The definitive answer is a condition violation.
It is not when you reach the end of the string. It is not a random arbitrary choice. You shrink the window the very millisecond the rules of the problem are broken.
Literally the exact millisecond.
If the rule is no duplicates, you shrink when a count hits 2. If the rule is at most 3 distinct characters, you shrink when the map size hits 4. The condition violation is the alarm bell that wakes up the realist.
Let's take a step back and connect this to the bigger picture. We aren't just memorizing algorithmic templates to jump through hoops on a whiteboard. We are training to be AI and ML engineers.
Very true.
How does this rubber band pattern actually apply to real-world machine learning systems? Because in the field, we are rarely dealing with static, perfectly clean arrays.
No, we are dealing with continuous streams of information. It's messy.
A variable window fundamentally tracks dynamic patterns in streaming data. Let's look at a natural language processing example, specifically chunking text for a large language model context window.
Oh, this is super relevant.
You are feeding an LLM a continuous stream of tokens. You constantly expand the context window that your optimist, pulling in more conversational history.
But LLMs have strict token limits, say 40196 tokens, or they have semantic boundaries where the topic drifts too far from the original prompt.
So when you hit token number 4097, or the semantic drift exceeds a threshold, your condition is violated. Your realist pointer activates and starts dropping the oldest context from the beginning of the prompt.
So it's literally sliding along the conversation.
Exactly. It shrinks the historical data just enough to allow the new relevant tokens to fit within the computational constraint. It is the exact same expanded contract mental model.
What about a cybersecurity application? Like parsing massive server logs in real time. You want to detect a cyber attack, like a DDoS attack. You aren't looking at the whole log at once. You are scanning a stream.
You would use a dynamic window to find the shortest period of time where error rates exceeded a critical threshold.
Okay, how does that work?
The optimist reads the incoming server requests. The hash map tracks the frequency of error codes. If the error count spikes above your threshold, the realist shrinks the time window to pinpoint the exact localized burst of the attack.
This is highly practical engineering, which means when you are in that interview, you don't just want to silently code, you want to demonstrate that you think like a systems engineer. Let's give our listeners the exact think aloud script.
Oh, this is crucial.
When they are standing at the whiteboard, markers in hand, what should they be saying out loud?
You want to project structural thinking. Say exactly this. We will use a two-pointer variable window approach to manage our state. The right pointer will act as our expander, continuously adding elements.
Nice and clear.
If our problem condition breaks, our left pointer will shrink the window until the state is valid again. Because each element is processed and removed at most once, our time complexity will be strictly amortized O of n.
That is incredibly smooth. Until the state is valid again. It shows you understand state management, pointers, and amortized complexity in 3 sentences. It proves you are a senior candidate.
It really does.
But, people still stumble under pressure. When you are evaluating candidates, what are the common mistakes to avoid?
There are 4 main pitfalls. Number 1, we already covered deeply. Panicking and assuming the nested loops mean O of n squared complexity.
Right, the interviewer's trap.
This panic makes candidates abandon the optimal path and try to invent wildly convoluted alternative solutions. Don't outsmart yourself. Trust the amortized O of n.
Good advice. What is number 2?
Failing to properly manage the data structure when shrinking. Sometimes candidates move the realist pointer forward, but they forget to actually decrement the count in the hash map or remove the element from the set.
Oh, that's a silent killer.
The window visually shrinks, but the underlying data is corrupted.
To use our analogy, that's like forcing the suitcase zipper shut, but the heavy winter coat is somehow still magically taking up spatial volume inside the bag. That will completely crash your logic on the next step.
Perfectly put. Number 3 is using the wrong data structure entirely, like trying to solve an at most k distinct characters problem with a basic set.
Because a set can't count.
Right. A set simply cannot track frequencies, so it cannot tell you when a specific character count drops to 0.
And the final mistake?
Losing track of the condition logic itself. The condition that triggers your shrinking loop has to be the exact opposite of a valid state.
Wait, explain that a bit more.
If the problem asks you to find valid states, your inner cycle must explicitly handle the invalid states. Mixing those up leads to infinite loops or windows that instantly collapse on themselves.
If we connect all of this to the overarching framework of data structures, learning this variable window feels like a major milestone. Where does this place a candidate in their overall algorithmic journey?
Mastering this is the pinnacle of the subarray toolkit. Think about the progression of an engineer. You start by learning brute force, which teaches you how to explore every possible option using rigid nested loops.
It works, but it's painfully slow.
Very slow. Then you graduate to Cadene's algorithm, which teaches you how to optimize decisions, like learning when to abandon a negative trajectory and start fresh.
Okay, stepping up.
Then you discover the fixed window, which optimizes structure. You learn to slide a rigid box efficiently without constantly recalculating the data trapped in the middle.
And finally, you arrive here, the variable window.
Exactly. This gives you dynamic control. You aren't just exploring or deciding or structuring. You are reacting to the data itself, expanding and contracting based on real-time, real-world constraints.
It's responsive.
Once you master the dynamic rubber band, you can confidently tackle almost any contiguous subarray or streaming problem an interviewer throws at you.
Let's recap what you've achieved in this deep dive. You have mastered dynamic window logic, understanding the fundamental tension between the optimist adding data and the realist shrinking the boundaries.
A huge leap forward.
You understand that an inner cycle doesn't always mean terrible performance, thanks to the turnstile logic of amortized analysis. You know exactly when a simple set is enough and when to upgrade to a hash map to track frequencies.
And you have the master template memorized, and you have the think-aloud script ready to execute under pressure. You even understand the mechanism behind LLM token limits and DDoS detection.
But we aren't going to let you leave without a challenge. We want to test your new mental model. So here is a final provocative thought for you to mull over.
Oh, I love this part.
We've talked extensively about strict conditions. No duplicates allowed, at most K distinct. But let's look at a level 3 practice problem from the toolkit.
This is a fantastic puzzle. The problem is, find the maximum consecutive ones in an array of ones and zeros. But you're allowed to flip exactly one zero into a 1.
Max consecutive ones with exactly one flip. I want you to think about our suitcase analogy again. How does the realist pointer behave when your window is actually allowed to break the rules exactly one time before it's considered a true violation?
Yeah, when does the rubber band actually snap back?
Think about how you would code the trigger for that specific allowance. Good luck in your interviews and keep stretching those windows.